Okay, so we're going over the 2015 practice exam questions, multiple choice questions here. This is number 3. Finding the integral here, just as a quick review, because we've already done this one. This would be a candidate for u substitution because we have x cubed as a part of the inner function, and the derivative would be 3x squared, which we have a portion of the derivative there as well as a multiplier. So this is going to be u substitution, and there's the work for number 3. The answer would be E. Again, I'm just doing these ones real quickly. Number 4, left Riemann sum. The big thing we pulled out of this one was the intervals are stated here, so that's just these intervals that are listed on the graph. And if they don't tell you the intervals, you can, if they don't tell you the intervals, you can assume that these could be intervals if they don't specifically state. The big thing was left Riemann sum. So you have to make sure that the left corner of the rectangles, the left corner is going to be a function height. And so 25 is your width, and then the left corner of the first rectangle would be a height of 4. So that's why we did 25 times 4. Then we did 5 times 6, and then we did 20 here, the difference there, times 8. And add those up and you should get 290. Yeah, 290. Okay. What's next here? Do you guys want to do 5? I guess we only got 3 more. Let's just rifle through them, hey? Okay, so number 5. I have to clip this out here. So this one is a piecewise function. Okay, and let's just see. So this one says, let f be a function as defined above, where c is a constant. For what value of c, if any, is f continuous at x equals 2? Okay. Any idea how did you guys do this? Any offerings here? How did you do this one?
You set the two functions equal to each other, and then solve, and then plug in 2 for x and solve.
Okay. So in order for it to be continuous at 2, that means that this function evaluated at 2, or as x approaches 2 technically from the left, and this function as x approaches 2 from the right, have to have the same limit, right? They have to be continuous, so they have to meet each other here. If the limits, the left limits are not correct, are not the same, then it's not continuous. So you take the functions, let them equal each other with 2 as the value for x for both of them, and then you should you can adjust the c, or solve for the c that will make those two functions come to each other. So that's maybe not the most efficient way of explaining that, but you want x squared sine of pi x to equal x squared plus cx minus 18. So it's got to be continuous at 2. So these should be the same when x equals 2, right? So we're going to put 2 in there. That's 2 pi, I guess, equals 2 squared plus 2c. And we do have some latitude here then, because this c obviously can be adjusted, right? It's a variable. So we can adjust c so that they are equal, and we do want those graphs to touch. Okay? All right. So this is going to be 4 times, what's sine of 2 pi?
0.
Yeah, 4 times 0, that's going to be easy. And this is going to be 4 minus 18 plus 2c. So 4 minus 18 would be negative 14 over here. It'd be positive 14 over here, right? Equals 2c. So I get c as 14 divided by 2, or 7. So 5 looks like the answer should be B. How you doing with that one? Good? Okay. All right, so hopefully there's just little mistakes here maybe that you're making if you're not getting these. These are a bit on the easy side, to be honest. These are the first 7 questions of the exam, and usually those are some of the more basic Calc 30 concepts. Now it's been a while for you guys. I get that. It's been a while since you've actually done some of this stuff, so this is good that we're going over it. All right, so don't be discouraged if you missed it, but this is why we're here today on a bright, sunny Saturday morning.
Sunny?
Well, it's slightly overcast, but the sun is shining. Beyond the clouds, the sun is shining. Remember that. Okay, number 6. Which of the following is an antiderivative of secant, 3 secant squared x plus 2. Okay. Well, an antiderivative, okay, so it's one thing to take the antiderivative of the function. You could do that. If you were freaked out about it, or if you panicked on the exam and said, oh my goodness, I don't know how to take the antiderivative of 3 secant, well, what you could do is take the derivative of some of these and just see if it matches, right? You could start with the options and then take the derivative and see if what matches. You could do that. Now, so there's two ways to kind of approach this one then. So what do we, when you look at this, what jumps out at you? Like what are some of the things that, and let's talk it out here so that we can share knowledge with each other. Is taking the antiderivative of this pretty straightforward, do you think? Or is there, like, what jumps out at you? When you see 3 secant squared x plus 2 as far as an antiderivative, anything jump out at you?
The derivative of tan is secant.
Okay, thank you. The derivative of tan is secant squared x, or the antiderivative of secant squared x is tan. Okay, okay. Now that's good, that's good. So we have a 3 here. We have a 2 over here as well. So tan, okay, I like tan. Let's start there. So the derivative of secant squared x is tan x. So if I took this derivative, I would just get secant squared x. How do I factor the 3 in there? Should I just put the it's a constant. So does it make sense just to throw the 3 in front? Yeah, because the derivative of this would be 3 secant squared x. Okay. Now plus 2, can we just, this is a separate term, so can I take the antiderivative of 2? Yeah, I should be able to. What's that? 2x, so it's a plus 2x. Okay. Now, do I see that here? I do. I do see that here. So is that going to be, wait a minute, 3c, oh, sorry, it's over here. I read that wrong. It's over here. Are you satisfied with that? Okay. Following. Yeah, okay. So here's the thing. If they asked you to take the antiderivative of this, then you would have to put plus c. Now, is it incompatible with, is this question in error because there's no plus c? No, it's not, because plus 0 is a valid antiderivative of this. Okay, so if you were taking the antiderivative, you would say the antiderivative is 3 tan x plus 2x plus c. Good job. But if they say which of these is an antiderivative, they could have put anything behind here, right? Plus 3. They could have put anything behind here to mess you up a little bit more. They could have put any constant behind there. And beware, this is a practice exam question. On the real exam, they might do just that, because they do save some of their best stuff for the real exam. Okay? So just think about that. Like, oh my goodness, where do all these constants come from? Oh yeah, right. The derivative of a constant is 0, so it doesn't matter what it is. Got it? So B, are you okay with B? I believe that's the correct answer. To be or not to be, 6B or not to be. Yes, 6B. Good. And finally, 7. Let's take a look at 7, the last one on this little assignment here. So it says if f of x is x squared minus 4, and g of x is a differentiable function of x, what is the derivative of f of g of x? Wow. That's the kind of questions you're going to get. Some of them are going to be really confusing. They're going to try and trip you up. Okay? So we're going along this at full speed here. Okay, this is real time. So we've got a function. G is a differentiable function of x. Okay? And so g is the inside function here. It's the inside function of f. Oh, that's interesting. Okay. So what's the derivative of f of g of x? Well, this looks like a chain rule, doesn't it? Okay. So if we were to take this, the derivative of the outside function would be f prime. We are supposed to leave g of x in there, aren't we? We're supposed to leave the inside function alone and then multiply by g prime of x there. Right? That's a, okay. So now, what about the fact that this f of x function looks like this? So f prime of g of x. Okay. So this is f prime of x. Don't really know what g is, so g prime of x. Some of the answers have g prime of x in there, so that's kind of nice. How do I reconcile this right here? Okay, so we put so take the derivative of f. I'm seeing this right here. What's the derivative of f? Just curious. It's 2x. Okay. So if it's 2x, that's when x is just x. So here, this is g of x. So would that make sense that this would look like this? So we'll put g of x here. See that? So that's actually 2g of x times g of x. So do we have anything that looks kind of like this? Or are we...
I mean, I'm sure the options look like that.
None of the options look just like this.
Yeah. No, I mean,
So d is 2 of g of x times, yeah. So that does look just like this now, doesn't it? 2, I guess the brackets are a little bit funny, but yeah, 2g of x times g prime of x. That's what we have. So you guys okay with that? That is correct. D is correct.
Wait, so like when you saw that the derivative was 2x,
Yep.
and then you saw at the end that like g of x was like x, that's how you just
Right. So f prime of x here is x. Is 2x. Right. That's for here. Now if inside the function we're after, it's actually g of x is inside here. So let's just replace x with g of x. So then this is 2 of g of x. Yeah. Do that.
the way I did it was I started with x squared minus 4, and I substituted in g of x, and then just did the derivative. Like
Okay.
instead.
Okay. Yeah. So that's great. So the other way, so the way you did it was g of x. You put that in right away, so kind of like we envisioned that here earlier. So g of x all squared minus 4. Okay. And then you took the derivative of this,
Yeah.
just the derivative of that. Yeah, so 2 g of x. And then, of course, you got to do chain rule, so it's g prime of x there. And then minus the derivative for is 0. So yeah, that's great too. If you substitute that first, maybe that's a little more straightforward. I don't know. That's good too, yeah. Okay, any questions about those ones? So for question number 4, this is a differential equation question, and the first part is slope field. So literally take a point like 0, 0, plug it in here, and get your answer. Anything that has x equals 0 should have a value for 0. And so the scoring is you get 1 point for the 0 slopes. So there should be 0 slopes, looks like here. So if you have all of those, you get 1 point. And the other slopes, these would combine for another 1 point.
So
Question?
what happens if there would be a 0 slope on the x-axis, so you just didn't draw the 0 slope,
If you did not draw one of the 0 slopes, you wouldn't get that point.
even if it's on the x-axis?
Even if it's on the x-axis, yeah? Why would that be an issue?
Because you wouldn't see it. Not really.
Yeah. You would have to draw it so you could see it. Yeah, you have to draw it so you can see it. If you leave it blank because, it's 0, it's just going to be, it's right on the axis. You can't say that because you didn't draw anything that it's there.
Okay.
You know what I mean? No. So you're going to have, that's why you use a number 2 pencil on this, so that it's thicker than the lines. And even if you're having trouble with that, even if you've got it sharpened to a point that, you could impale an ant, then you're still going to have to make that line thick enough so they can see that that's a 0 slope there
Right.
somehow. You know what I mean? Okay? Yeah. So yeah, if you don't have all of them, you would technically lose a point there. Okay, what about B? What about B then? Let y be f of x be the particular solution to the differential equation with these initial conditions. F of 1 equals 3. Write an equation for the line tangent to the graph at f at the point 1, 3 and use it to approximate 1, 4. So there's a few layers to this one, right? And this is why takes 15 minutes for you get 15 minutes for this question. You only have three parts to it, right? So approximately 5 minutes each part, let's say. So this one is got a few things. So you've got f of x is the particular solution. So you're gonna have to first of all find that with the initial conditions. Okay? All right. So you're gonna have to separate your variables here. This is a separable differential equation, right? So this y minus 1 is gonna have to go down in the denominator, and the d of x is gonna have to come up here. So wait a minute, is this a?
I did not realize that.
All right, so we just discovered that the way this is laid out, there's a space for A, there's a space for B there, but yes, A, B, and C are all connected to the original question. So we had some in the class that thought these were totally separate questions and were very confused, and I would be too. So yeah, so let's actually, do I have a,
I'm surprised you
the-
got an answer.
yeah, so, surprised you got an answer. Okay, yeah, so this is what it looks like for you guys, right? So B is, is connected to, this is the question 4, so that you'd be referring back to probably parts of the original question there, yeah, for these ones. Okay, dokie? Okay. So this is no calculator allowed. So let's just, let's go ahead and, FRQ4, hang on. Okay. So let's go over separating the variables here, shall we?
Wait, can't you just use the slopes from the slope field for the
I
derivative?
think you do that on C.
Like
They
on
want
C
you to
you,
find-
on
Yeah.
C it makes you,
Uh,
on C it makes you like actually solve it, but for B you can just use the slope field, right?
Okay, find the particular solution. Oh, yeah. So yeah, they have to do it in C for sure.
But for B you
Um,
can just use the slope field.
Yes, you can use a slope field for B. Right. You're gonna have to do it either way, but you're right. You don't have to do it for B. So let's just, okay. So let's take that approach for sure. Yeah. So it B. So f of x is a particular solution to the differential equation with its initial conditions f of 1 of 3. So 1, 3 is going to be this one here, and we already said that that was a what, positive 1/2 slope. So f prime of 1 is 1/2, positive 1/2. Okay, that's gonna help. Now for this one, that's all you need to know, I guess, and that's all you need to know to do this estimation. So linear approximation. So for C, you're gonna have to find the particular solution, but for B, you're right, you can just use the slopes on the graph. So that is an important note. So what's the linear approximation? Was it L of x equals what? F of A plus F prime of A times x minus A. So we're basically taking a starting point, f of A, and in this case, we're going to take f of 1 equals 3. Let me make this a bit bigger for you somehow.
I just
But not too
realized
big.
it says make an equation for the line tangent to the graph of f of x.
Yeah, write an equation for the line tangent and use it to approximate f of 1.4.
So I didn't actually do that. So like I just realized if we just do the linear approximation, it's not technically just the tangent.
You do have to have an equation
Yeah.
for the line tangent, and you have to have the linear approximation of this one. So how is that different than from C then? Let me look back, find the particular solution. Given differential equation with the conditions f of 1 is 3. Okay, well, write an equation of the line tangent and use it to approximate. Okay, so still, let me just move this down for now. Okay, so let's write an equation tangent. Well, we still know that f prime of 1 is 1/2, right? So the equation of the tangent line is going to be we're going to have y minus y1 equals m times x minus x1, right? So that's our point slope form. We do have a point, that's 1, 3, and we do have the slope which is 1/2. So let's go y minus 3 equals 1/2 times x minus 1, which is going to be y equals 1/2 x. That's going to be minus 1/2 plus 3 is going to be plus 5/2, I guess. Okay, so write the equation of the tangent line. That's the first part. Does that look good to you guys? The solution, now let me get back to the solution here. If I can find it, give me a second. What's that? Question number 1, 2, 3, 4? What are we? 4. Hello. Okay, yeah, so y equals 1/2 x minus 1 plus 3. So we simplified that. Okay. The derivative, what they show here, the derivative, what they show is going from the original differential equation. They plug in the points 1 and 3. Now, we did that for the slope field to get the 1/2. So you're right. If you remember the slope there, they're just saying this is how you find the slope of 1/2. The equation is going to be this one. So the tangent line equation is worth a point. So we do have to make sure we have that. And then the approximation. So this line, okay, so there's 2 different ways of doing this. And this is good that we talked about this and we're going over this question. Because the 2 different ways of doing this to approximate the 1.4 is you're gonna go straight to here, the linear approximation, right? Or what this is really leading you to is here's the tangent line slope. So let's just say, I don't know what this looks like exactly, but let's just say that here's the tangent line, okay? We use the slope to find the rise from this point to the next point. So we use the rise here to get the linear approximation of this point. You could also just plug in your x value, your new x value, and find out what the y value is because it's on this tangent line. You see that? So we actually, because the way this question is framed, we do have to find the equation of the tangent line, which we did, and we have to use it, not really this linear approximation, I guess. We have to use this. So we're just saying, hey, what is this x value on this line? So I guess it would make sense to just put in, so I think we just put in y equals 1.4 into this equation here. And then find out what that y value is.
Wait, 1.4 or 0.4?
Well, again, this is, so we're not doing x minus a, so we don't just plug in the difference. We actually plug in the value of x, whatever x is that we're looking for the y value for. So I think that should be 1.4. Yeah. Okay, the question is, would this be okay right here? Just this y equals, would that be okay for just not simplified? I don't know, and I don't think so, but that's a good question.
Put it in the format that the linearization formula is. That would be okay, right? Or would it be? Wouldn't that even fit with 2?
Maybe like.
Okay, so further to that question, what we found on the internet here from the College Board, in general, answers like 2 plus 3, you could leave as 2 plus 3 instead of writing 5. You could leave it like this expression instead of writing the simplified. Another comment said, if you can do it on a calculator without taking an absurd amount of time, you probably should do it. So going back to this, I hate to give you a wrong, a bum steer here, but notice that in the answer key, they did not leave it like this. They didn't. They simplified that to 3.2 decimal. So I think an expression, you can leave an expression. Obviously, this equation of a line, I expanded out. I did y equals mx plus b. They did not. You could probably leave it in the slope point slope form. So that's an expression you probably wouldn't have to simplify. Good. I think if it comes down to the numerical, you probably should go that extra step. It's not an absurd amount of time to do that. Now, granted, if you go from here to here and you get your number wrong, then you don't get a value for the approximation. But I can't guarantee that they will take this alone. I just don't know.
If it's like one term, just something multiplying.
Yeah, if it's one term, if it's 1/2 times 0.4, you can leave that.
Okay.
Yeah, for sure. That would be fine. Even though that would be pretty easy to fall through on. But yeah, that's one of the things I found for that. But you're right, that's a good question. So we'll finish that to 3.2. Let's keep going with this question then. All right. So 3.2 or in fraction form or whatever. Now that is what we get, right? 0.7, 2.5 plus 0.7 is 3.2. Yeah. Okay. All right, so that's B. And then what about C? So I think C is just find a particular solution, right? So this is where we do the separation of variables, I guess, then. Okay, so we'll just take a look at the answer key here and assess the points here. So separable differential equation, yeah. So the x over 4 can stay on the one side. The y minus 1 has to go down here in the denominator, and the dx has to come up here. So we end up having 1 over y minus 1 as an expression.
Wait, how do we just get y minus 1 over there? Do we just divide?
Okay, sorry, how does this y minus 1 get over here? Yeah, we're dividing by y minus 1. And then you're bringing up the dx up here.
I was thinking you would, well, first of all, I didn't even know that you did this, so this is just what I'm thinking now, because I just, but I got 4 over y minus 1, because I wanted to put the 4 on the one side and divided the y minus, I don't know, I think
So what you want to do is you want to take the factor with an x and the factor with a y and separate those factors. You don't want to separate the individual terms necessarily. Yes, question?
So I separated the variables. I just separated them totally wrong. Like,
Oh, okay, what did you do?
multiplied both sides by y minus 1. And somehow
Oh, you did?
I canceled out the y minus 1 on the
You multiplied both sides by y
Yeah,
minus
yeah,
1
so-
and
so I-
instead of y minus 1 squared over here, you just cancel them out to 1?
Yeah.
Okay.
So I had the integral
Okay.
of y minus 1 dy equals.
Right, so you would basically get 0 points
Yeah.
on this
So-
question.
Okay, that's great.
Yeah, unfortunately. So if no separation of variables, you get 0 to 5 for sure. The separation of variables, yeah, antiderivatives. Now, gee, this is another good question. I don't think they would give you any points for that, but
Sure they won't.
but the antiderivatives. So I believe that the antiderivatives for the proper separation would be what you get 2 points for. I don't think that if you separated the variables improperly and then did proper antiderivatives of
No.
expressions that were incorrect, I don't think you get any points for that. So I'm pretty sure if you didn't separate them properly, then I'm pretty sure you're hooped on this question. I think so, yeah. Because even like if you get something wrong and do the correct antiderivative, I don't think you'll get a couple points. I just don't think they're that nice, really.
Total of 1 out of 9 on this.
So let's just work through this then. Of course, the integral of 1 over y minus 1 is ln of y minus 1. And because there's no number in front of y, we don't have to divide it by any constant, right? It is absolute value, so that will come into play later when we include our initial condition. Because we might have to put plus or minus somewhere when we get our y, whatever by itself, right? Or our e expression, I should say. So 1 over 4x, the antiderivative of that would be, we're going to have an x squared there, and then you're going to divide by 2 again, so it's going to be 1 over 8x squared plus c. So a reminder, we don't need to do plus c on both sides. We will do one combined plus c when we're solving for these. Good idea to right away put in your values now. So what was it? 1, 3? Was that the point? 1, 3. So if I put 3 in for y, I get ln of 2 over here. If I put 1 in for x, I get 1/8 plus c. So c is going to be ln of 2 minus 1 over 8. That's what the c value is going to be. And you don't combine those to a decimal, just, I guess, leave it like that. We're going to do kind of exact as we can. So just this is your constant. So there it is right there. We've inserted it there. So now to get from this step here to solving for y, because you have to solve for y, so then we exponentiate is what it's called. And because this is a base e down here, we have to rewrite it as e to the power of all this. So e to the power of all this equals, and I think they maybe skipped a step there, But it's e to the power of, x squared over 8 plus ln 2 minus 1/8. And then that equals this absolute value of y minus 1. I guess as far as the absolute value goes, you're going to have to test to see whether this should be positive or negative at some point here. Because we have 1, 3, so if 1 goes in for x here, would this be a negative 2 or a positive 2? You could, I think, deal with the absolute value signs there right away, or even before this step. I see hands. What?
What happened to the 1/2 in there?
Oh, yeah.
What happened to this over here?
Like
I think they just simplified it. Are you talking about this right here, this part?
yeah.
So they took out, you see how there's a 1 over 8 in both,
Oh, wait,
Uh,
sorry.
yeah,
Huh?
this way.
They just put it-
Wait, I think, did I put something? Did I miss an 8 here? That's supposed to be 8, not a 2?
Is it? Oh, okay.
Okay, so,
Oh, okay. Oh, so they took the long 2 out and then just put everything over 8 instead.
Whoa, wait, so they did.
This is like, it's divided by the same thing.
Yeah.
X squared over 8.
so, yeah, so what they did now, okay, so let's just keep going with this thought here. So this is going to be positive. If you put the x and y in at any point here, this should work out to be positive, okay? So a 1, and this is going to be a positive value over here. Okay, so when you add, so we have 1, 2, 3 things that are added or subtracted as exponents. So remember, that's the same as writing e to the x squared over 8 times, isn't it times when you multiply, right? So times e to the ln 2 times e to the negative 1/2.
Times.
1/8.
Oh, sorry, 1/8. I've zoomed in so much, my pen is so thick. My bad. I'll zoom out a bit.
Oh, yeah,
Right, so it's same as multiplying that. Now e to the ln 2 is just 2. So that's where they get the 2 from. Now they've got a common, now you've got, well, this really, x squared over 8 minus 1 over 8. And so they took an 8 out now. Yeah, so e to the 1 over 8 times x squared minus 1. And so that's really what they have here, right here. Now the plus 1 comes from this, right? You add 1 to both sides, so add 1 to both sides, and that's how you get your y.
Oh.
So we didn't do that, but add 1 to both sides to
Where do you
get.
say, for all x, is there a mark for that?
I don't think so. For all x.
Would that count as part of the solves for?
Let me just see here. So separation of variables, getting the correct antiderivatives, the constant of integration, so that's the c value, you get right, using initial conditions, and then solves for y. So those are 5 points right there. I believe that's what you get your points for, just kind of right there. And your question was, sorry, what?
Like where it says the y equals whatever for all x.
Oh, for all x? I don't think you need to put this in there for points, no.
Okay.
No. I don't believe so. It doesn't say anything in here about that. So if there is a restriction on the variable, then maybe you would say for, x not equal to or something, or x greater than 0 or whatever, if that was the case. But because it's an e function, right? It's an exponential function, so right, it's xer generally. So if x is not in a denominator or it doesn't cause any mathematical problems, then it's just xer. That's what they mean.
Yeah, what were
I don't think you get a point for that though. Question?
The line there where it says because f1 equals 3 and y is more than 1, that's how they determined that it would be a plus and not a minus for.
Yeah. So
That's
you.
an interesting method.
You're talking about this line here?
Yeah.
Because f of 1 equals 3, and so if y is greater than 1, then this has to be, then this would be a positive. Yes, I see, yeah. That's one way of doing it. So I think the way we did it, we just plugged in initial conditions and then added a plus or a minus on the absolute value side to make the equation true. So yes, this is another way to reason through that.
It looks a little bit faster. How did they-
Yeah, sure,
Huh?
yeah.
How did they-
So they're saying, so this y minus 1, is this actually a negative times y minus 1, or is it a positive times y minus 1? The initial conditions say that a y is 3, right? So if you put 3 minus 1, is that actually going to be a positive, value, or is that going to be a negative value? But y is greater than 1. So look at this. If y was less than 1, you see, then this would actually be negative inside. So you're looking at what is the value of this y minus 1 inside. 3 minus 1 is a positive 2, so this whole thing is a positive. If f of 1 was negative 2, then negative 2 minus 1 would be a negative 3. So you'd have to put a negative outside here in order to drop the opposite value signs. I would still just put in your initial conditions and see if you need to add a negative or positive to one side to make it true. So, okay, so that is that. Any questions? Okay, so we did 7 multiple choice there, and we did this number 4 on the 2015 practice exam. Okay, so we're going to do another one, a table free response question that says this. Water is pumped into a tank at a rate of WT is 2,000 e to the negative t squared over 20 liters per hour. Okay, so liters per hour, it says rate. So this WT here is a first derivative, right? Like an F prime. However you want to note that, whatever. Water's pumped into a tank, so it's going into the tank, okay, from 0 to 8. So it behaves like this at least from 0 to 8 seconds, which the context of the question looks like.
Or is it in hours?
Liters per hours? Yeah, what did I say? Seconds?
Is that
Liters per hour. No, sorry, I meant to say liters per hour if I didn't. Did I say something wrong?
No, I just don't know if that changes the question at all.
Well, we have liters per hour here in our table, which we haven't kind of got to this one yet. We don't know what RT is. We know what WT is. So let's keep reading. Where T is measured in hours, okay, water is removed from the tank at RT. Okay, so RT is removal. There we go. So W is going in, R is removal. So removed from the tank, liters per hour. That's another rate, okay? R is differentiable, great, and it's decreasing from 0 to 8. So the rate per hours of removal, you see it's going down each time. So it is decreasing. So we've got a rate going in and a rate going out. Selected values of R of T are shown in the table above. At time T0 there are, okay, so at T0 there's 50,000 liters of water in the tank. So we have a bit of a starting amount. And so if water is being removed, the integral of this first derivative, this integral of the rate, is going to be the total amount of liters involved in being removed, okay? So we've got a starting point. The integral of this over any time period here will be the change in liters in the tank, okay? So estimate from the tank, looks like, estimate R prime of 2, R prime of 2. So this is, R is the first derivative, so this is really the second derivative. Estimate R prime of 2, show the work that leads to your answer, indicate units of measure. Okay. So if we have something like this, let's say, I don't know if this is straight line or not, but the area underneath the graph is the antiderivative, right? The derivative would be, looks like we're looking for the slope, or the estimated slope of the tangent line, okay, the slope of the tangent line at 2. Was there a hand up over there? Yeah.
Do we have calculator in this?
Oh, good question. There's a calculator here or not? I don't know. We're going to try and do it without a calculator. I think this would probably be without.
Huh?
The answers in the sheet are kind of.
The answers are decimals. Yeah,
not
we'll.
decimal, but just precise.
Yeah. Okay. Well, we'll see. We'll see. Yeah. I don't know. Usually it'll say, I don't know where this is taken from. Yeah. I don't know. We might run into, with these equations, we might run into a calculator necessary to integrate or whatever these. Okay. So estimate R prime of 2. So we're trying to find the slope of the tangent line. And again, if we have some points, right, like this, our best guess for this tangent is to find the slope of the 2 neighboring points. That's our best guess. So we have 1 and 3. So we want to find the slope, the difference in y divided by the difference in x. That's the slope of those lines. So the slope here, which is going to be r prime of 2, is going to be 950 minus 1190 over 3 minus 1. And that should give you negative 120. So 950, yeah, 240 over 2. Now, you think it's pretty important to put your units in there? It does say it, and even if it doesn't say it, yes. So this is a derivative. We have units for a derivative here that we've used, so liters per hour. Liters per hour. Hours.
When do you only use square if it's an integral?
Liters per at liters per hour squared. Yeah. Because it's a rate of the rate. It's a rate of the rate. So liters per hour per hour. So that's liters per hour squared. And I think you can abbreviate probably liters and hours. So L over H R squared I think probably would be fine. Just make sure the squared. Obviously they're looking for the squared part, right? So it does say in the scoring key, it says the estimate. So this number is worth 1 point. And the units, getting that correct, is another 1 point. Okay, any questions about A? Okay, I'm gonna grab B. Let's take a look at B here. Come now. So use a left Riemann sum with 4 subintervals indicated by the table to estimate the amount of water removed. So remember we talked about that, right? If you have a graph that is a first derivative or a rate, the area under the graph would represent the total change in value of the original function, so the total change. So left Riemann sum from the water removed, to estimate the water removed during the whole 8 hours. And is it an overestimate or an underestimate of the total? Well, you'll have to figure that out. That's not too hard to figure out because we know that it's decreasing, right? So we know that these points are going down. So if it's a left Riemann sum, that means that these are what the rectangles look like. And is that an overestimate or an under? It's an overestimate, right? Because it looks like we have excess that we are counting. So it's going to be an overestimate. So if you figure that out right away, just circle it and remember to write that as part of your answer. So I'll get the table, maybe that table here too. You guys can go ahead and start working on that. Left Riemann sum, so you're going to take the width of 0 to 1, and then you're going to take the very first point as the left corner, right? So 1 times 1340, that's where you're going to start.
So for this, can we use our calculator to add that?
Yeah, I mean, if you don't have a calculator, you have to do it by hand, but now I don't really care. You can use your calculator. So you're going to want to write what you're doing. So the integral, it's an integral of this r function, right? From 0 to 8. Okay, so you should have an answer of 8,050 liters. So again, that is the...
Is the unit just liters?
Yeah, so estimate the total amount of water removed. So this is not the amount that is left in the tank because we don't have an initial amount that we're subtracting this from. We're just talking about the change. So the amount of water that's removed is 8,050 liters. Did you say you have to have a unit? You have to have units for sure.
Yeah, I was just wondering if it was just going to be liters, but that was it.
Yeah, should be just liters. Again, the question gives you liters per hour and hours, so the amount would definitely be liters. That's what we're referring to here. You bet. And then remember, state that's an overestimate. It does say explain why or give a reason for your answer. I see in the grading part here that you just have to say it's an overestimate because the function is decreasing. And I would, because we drew this little picture here, I would include that as part of your rationalization that, hey, I know that because here's the sketch of the LRAM and we have excess. So it appears that all you have to do is write this sentence, just because the function is decreasing, it's going to be an overestimate, but I would include this little diagram if you drew that. Okay, so here are your two answers, this one and this one here for B. So C says, use your answer from part B to estimate the total amount of water in the tank to the nearest liter at the end of 8 hours. Well, as I just mentioned, we just calculated the change in liters. Wait a minute. Oh. Okay, so yeah, just going back to B, it says the total amount of water removed is 8,050 liters.
Frozen.
Oh, frozen, sorry. So that should be good enough. Just make sure that it's indicated either in the question or in your answer that it's removed. So if it says estimate the total change in volume of water, you'd have to make sure 8,050 liters removed.
Wait.
Okay? Or negative 8,050 liters change.
Water is being added though.
No, not for this one.
For C?
Okay. No, I'm talking about B here still. I'm on B here still. So I'm just saying, make sure that you know it's either in the question that it says the total amount of water removed. Your answer could be just 8,050 liters. Or if it doesn't say removed in the question, you have to make sure that they know that you know that this is liters being removed. Okay. So C, use your answer in part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours.
Would we subtract that from the 50,000?
Okay, hang on. So at the end of 8 hours, we know that there's also something else in play here, right? And that is the fact that we have water being pumped into the tank as well. So we have to consider that, use your answer for part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. You have to be careful not just to take 50,000 minus 8,050. Because in the question as well, there is a function for the addition of water, which we haven't taken a look at yet. So the total amount of water left at the 8 hours has to include the original amount you started with, the total amount of water that you removed, plus the amount of water that was added through this second function that was given to us. So, and again, this is where they trick you. I wouldn't say trick you, but this is where they add the layers to the question. They don't say anything about, hey, remember the function where water is being added, right? You have to think about the whole thing and say, okay, what about this other function that they gave us? That holds true for the full 8 hours as well. So I have to include that in my answer. So it's going to look like this for C. The volume remaining would be equal to your 50,000 liters that you started with, plus, well, actually, let's just do the minus first because we know minus 8,050. And then the representation of the water being added would be this integral from 0 to 8 of the function that is being added at Wt. dt. And in your explanation, you don't have to write out the whole function, just write out what the function sort of name, Wt. So that would be great for a first step. And then, you will need a calculator for this type of question. So maybe there is a calculator, this is calculator active probably. So make sure you grab a calculator if you don't have one yet, and then find the integral here. Find the value of the integral for this one, and I'll go back and copy, here we go.
Josiah, do you need one?
Sure.
Yeah. Actually. Mm-hmm. Yeah, I don't think they'd ask you to do this without a graphing calculator, I don't think. Although it is an E function.
The answer has decimals.
Yeah.
Yeah, it does, I know. So I think you need a calculator for this one. If it was just negative t over 20, you could do it by hand easily. But yeah, you'll need a calculator for this one, I think. Okay, so that should be your integral there. And when they say estimate, I think you can round it to the nearest liter. I see in the answer solution key here that they do have. I'll just flip over there now. They do have this rounded to the nearest. Wait, what? Okay. What is this? 16. Does this it here? Yeah. So they just have to the nearest liter there. Okay. All right. So let's take a look at D, and I'll just clip this answer here right now, so we can just look at the answer and go through this. Points, by the way, 1 for the integral, 1 for the estimate. Okay. So for D, what does D say there? Back to it a second. So D says, for the time 0 to 8, is there any time t when the rate at which the water is pumped into the tank is the same as the rate at which the water is removed from the tank? Explain why or why not. Okay. So, are there any places where the rates are equal? Okay, good question. Okay, so what do they have here? The rate at 0 and of going in and going out is greater than 0. So at the beginning, the water is being pumped in. There's more water being pumped in than water being removed. So the angle that they took here, which I can't get this on the same screen, sorry, very well, is that at the beginning, the rate was, and I guess what you could do is you could graph each one. That would probably be the best. If you have your graphing calculator, you can graph each one. If you don't have your graphing calculator, this would be the way to go, saying that, you know what, the rate coming in was greater than the rate going out. And then at the end, the rate going out is greater because the subtraction is less than 0.
No formula for R. We just have a table of values.
Yeah. We're given the endpoint.
Okay. So we are, yeah. So this is the rate here. So I guess, sorry, what you want to do then is for this W function, plug in 0 and find out what the rate is. And it's greater going in than 1340. And then at the end, this number 700, right, is greater than what you would have if you had 8 as t here. So with your calculator, you could find out those two rates. So, sorry, does that make sense?
Yeah.
Yeah. So if the rate, so graphing it, the rate coming in is higher than the rate going out, but at some point, because at the end they flip. So is there a point where, now, you would say these functions are continuous, both of these functions are continuous, and so for the intermediate value theorem, because they're continuous, and because there's a sign change in those differences, that there must be some point in there where they are equal, because they are continuous. Now, they're continuous because there's no restrictions on the variables, as far as we know, right? And by the nature of the problem, water being pumped in, you can't just have in an instant in time, water just appear out of nowhere in an instant in time. It is by nature of the problem a continuous function. So water is being pumped in. Even if you have an influx of water in that instant in time, there would be, the graph still would be continuous. You wouldn't have water all of a sudden appear. So the intermediate value theorem guarantees that that between the minimum and maximum, there are values for each, there are values in between those, right? For each value of x, there's a value that's somewhere in between there. It basically guarantees its continuity.
If they asked us to find the time, would we have enough information to find like the exact time?
Probably not, no. If they asked you to find the exact time at which they're equal, probably not, because you're only given certain values for the one function. You aren't given the actual equation of the function. So you don't know the values in between
We're just
the ones that are
looking for
given in the table.
information.
Yeah. Yeah, if there was a time on the table, like for example, if this function here at time equals 1 exactly equals 1190, then you could say, hey, that's the point. Or if you plugged in 3 into this function and it also equaled 950, then you'd say, hey, I found the point. It's here. Yes. So that would be the case where they would say, hey, where is it equal? And you're like, oh, I only have certain points. Well, those are the points that you test to see where the rate is the same for both coming in and going out. So that they could ask you that question. In that case, you'd have to see if one of these points is on that other function as well. Yeah.
It says considers W minus R. What do they mean by that?
Okay, so yeah, for scoring, let's go back down here again. For scoring for this, so it's continuous. Intermediate value theorem says that there should be one point where they are equal, or where WT equals R of T. For this value of T, the rate at which water is pumped into the tank is the same as the rate at which water is removed. The scoring says you're going to consider the fact that there would be a difference greater than 0 and less than 0, and then so there would be a point where they're equal. Answer with explanation. So quoting the intermediate value theorem, I think is what their explanation would be. You'd have to say, even if you didn't invoke the theorem, it doesn't say that you have to invoke the theorem, but because they're both continuous, and because the difference is positive and then negative at the other end, then there must be a point somewhere where they overlap or it's equal. So if you said that without invoking the intermediate value theorem, you might be okay, because it just says answer with explanation. I think you'd be fine. Now, but invoking this theorem, which is basically highly connected with just continuity, right? So because they're both continuous, the intermediate value theorem says that there must be a point there. Now, did that answer your question?
Yeah.
Yeah.
Is that last paragraph necessary?
Is the last part necessary to write? Is it for? I don't think so. But you would want to explain somehow that, putting all this together, you'd have to explain that because the rate of water going in is higher than rate of water coming out at the beginning, but the rate of water going out is higher at the end. Therefore, because they're both continuous functions, there must be a point, time t, where the rates are equal. So something like that. It worded exactly this way. I don't know. There would be some latitude there, I would guess. Okay. All right, that helps. That's a table question. Hopefully that helps. They could ask you slightly different questions, but at least you have an idea. And I think the most important thing is, hey, what is, is this table a rate? Is it a function? Is it an antiderivative? What is it? So that you can kind of know if you need to find a slope of a tangent line or if you need to find area underneath. If you can figure that out, then you're well on your way. Yeah. So just another question about arc sine. So as a multiple choice question, you might run into something like this, where here's f of x, arc sine of 2x. What is f prime of 4? So you got to remember the formula for derivative is 1 over root 1 minus x squared. That's the derivative of arc sine. So chain rule, plugging this in, this is sort of what you might get. But in multiple choice, you might have answers that don't match up with this. So for example, this is one of the multiple choice answers. And how you get there is you take out a 1/4 from this expression. That 1/4 as a factor is a perfect square. That can come out as a 1/2. So I had 1/2 out here. And then so you end up with 4 minus x squared underneath the root sign. That flips and multiplies. So you end up with this. So that was a question, I think, similar to that I saw in multiple choice.
Multiply top and bottom by
You could change this around different ways.
Yeah,
True.
It's just such an incredibly arbitrary.
It is, yes, it is. And that's, I mean, why would you end up with this? Well, because that's a version of the correct answer. You know, that is a manipulation of the correct answer.
Wasn't the first thing the same thing then? Just like-
Yes, this would be the same thing as this. But what I'm saying is that on the multiple choice responses, you don't have this as an option in the multiple choice response. Right? So this is what they do on the AP exam. They don't want to know if you've memorized the derivative of arcsine. They assume that you've all done that. But now they want to see is, hey, can you manipulate this algebraically? Like, do you see that you can change this around to match one of the answers that we have there?
Then they should have an open book.
Open.
Well, there's no sense complaining about the way they do things. I'm just telling you this is the way they do things, so you just have to be ready for it. But yeah, so if you don't see your original response, either you did something wrong, you got this wrong, or you have to maybe see if you can somehow manipulate your answer to make it look like one of the options. You could do it. It's not a big deal. It's not impossible. It's not impossible. Just use some space to do some scratch work. Just try a few things, and like I say, if you spend more than a couple minutes or 2 or 3 minutes on something, make a guess, fill in your answer, and then put a big fat star beside it or whatever, and come back to it. Like, just somehow remember that you have to come back to it. And so then if you get done to the end, if you do have any extra time, which chances are you're not going to have a lot of extra time, these things go pretty quick. So most students run out of time before they have extra time to go back and look at things. But if you do, you have a chance, go back and maybe with some fresh eyes, now that you've thought about something else, or maybe you've run across something that's given you a hint, then you can maybe take another look at that. But don't leave anything unanswered and put a star beside, you know what I mean? Because you might not get back to it, and then all of a sudden you get it automatically wrong. So at least make a guess before you come back. Okay? All right. Anything else right now? All right.
After you answer it, you're trying to do like